Okay, so you plugged it in your calculator and sketched the graph over there. It's a cube root function, so the sketch is there. So we're going to explain obviously looking at it, it's continuous. So we're going to explain why it's continuous. So I have f of 0 is defined and it equals 2. So the important part is that it is defined at f of 0. That's part of the definition of continuity. So the second piece, remember we had to say, does the left-hand limit as x approaches 0 equal the right-hand limit? In fact, they do. They both equal 2. So because as we're approaching 0, we're reaching 2 from the left and from the right. So the limit, the overall limit at f of 0 exists. And then the third part is the defined point and the limit should be the same. And they are. So f of 0 equals 2, and that equals the overall limit. Therefore, f of x is continuous at x equals 0. Now the next thing they ask us to do is to find the derivative. So I'm going to find my derivative. I have f of x equals 1/3 plus 2. That's my function. And then this one's easy. We just use power rule, and we get the derivative at f of x is 1/3 x to the negative 2/3 power. And you can write that as 3x to the 2/3. And then plug in your value of 0. So I plug in here. And again, because 0 times anything is 0, it is undefined. So f of x is not differentiable at x equals 0 because it is undefined there. Alright, so let's try the next one. You plug it into your calculator and you get a graph that looks like this. These are the ones that I think look like birds. You remember when you were a little kid and you used to draw birds? That's what they look like. Alright, so obviously looking at it, it's continuous. I could start this with my pencil, draw it, never pick it up. But we have to explain with the three-part definition of continuity why it's continuous. First of all, f of 0 exists. It is defined at 2. Then we defined the left-hand limit. As x approaches 0 from the left, it equals 2. As x approaches 0 from the right, it equals 2. So the left and right-hand limit are equal. That means the overall limit exists and equals 2. And then the last part of the definition is that the limit as we approach 0 has to equal the defined point of 2, which it does. So f of x is continuous. So now we're going to find the derivative. Another easy derivative because we just get to use power rule. So it's 2/3 x to the negative 1/3. And then if you want to write that correctly, put your x on bottom and make it a positive 1/3. Plugging in 0, it is undefined. F of x is not differentiable at x equals 0 because the derivative at f of x is undefined. So when we were doing this the other day, somebody said, I kind of feel like this bottom one wasn't even necessary because it's so similar to the top one as far as even the values that you got and everything. But it is because of what comes next. We're going to explain what all of this means and what we just discovered. So the first thing is, at the very top, they ask us to, based on what we have seen about continuity and differentiability, what does continuity imply? Or does differentiability imply continuity? So the first thing is, continuity does not imply differentiability. As we saw in those last two, they were both continuous, but neither one of them could be differentiable. This is the reason why. Because at an order, at a point of inflection, or a cusp, a continuous function is not differentiable. So let me explain to you real quick what a point of inflection is. And then obviously, I think after we explain a point of inflection, it'll make sense what a cusp is. If you have a graph, let's just say it's a sine wave. And it looks like this. You know how sine waves look. I'm going to write it in two colors though. But just think of it, it's just a sine wave. It's up and then down. But this first piece is concave down, and the second piece is concave up. The point where the two things meet, where it switches from being concave down to concave up, or vice versa, that is called a point of inflection. So I could have another one right here. Remember, this is still a sine wave, so it's just going to keep repeating. These are both points of inflection. It doesn't matter if it's switching from down to up or up to down. If the graph is symmetrical, the point of inflection is really easy to find. But on the graph that we just did, the cube root function, it has a point of inflection. If you look, right here, this first piece is concave up, and then right here it switches to being concave down. That is a point of inflection. So that is why it is not differentiable there. Now, a cusp is what we would call a sharp edge. So this point is not a point of inflection, because see, we're concave down and concave down. But this is what we call the cusp. The same thing would happen, let's say back to our sine wave. Let's say right here at the end of this sine wave, it all of a sudden just zooms into a linear function. This is a cusp, where it switches from having curvature to being straight would be considered a cusp. Any sharp point on the graph is considered a cusp. Okay, so continuity does not imply differentiability because of that, because of points of inflection or because of cusps. So the second part of this is, but just because continuity does not imply differentiability, the function must be continuous at the point to be differentiable. So in order for a function to be differentiable at a value of x, two things must be true. F of x must be continuous, at x equals a. We're going to say a is our, it's just any value. A is representing a constant number. Then this must be true. The limit as x approaches a of the derivative of the function must equal the limit as x approaches a from the right of the derivative of the function. So the derivative has to equal the same thing from the left as it does from the right. So let's look at this one and we're going to consider what that means. I think it'll make more sense when we consider it. First thing is g of x continuous at x equals 3? Well, let's check and see. Make sure that it is continuous. In order for it to be continuous, the point has to exist, which it does because there's an equal sign under this. So let's plug in. G of 3 is going to be square root 3 plus 1. So g of 3 equals 2. So that's the point. That's the first part of the definition of continuity. Now we have to check it from the other side and see if it also equals 2. So I'm going to plug in from the other side, g of 3, 5 minus 3, so it equals 2. So the limit as x approaches 3 from the left equals 2. The limit as x approaches 3 from the right equals 2. And the point is defined. So g of x is continuous at x equals 3. So g of 3 equals 2, which equals the overall limit. I'm just writing this because if it was a free response question, you want to get as much in there as you can. Make sure that you're getting the correct definition. So The overall limit exists because the left and right hand limit both equal 2. The overall limit equals the value of the point, so that proves that it is continuous. So now, is it differentiable at x equals 3? Well, in order for it to be differentiable at x equals 3, the left and right hand derivatives have to equal each other. So we're going to take the derivative of each piece. So I'm going to find the derivative of both the left and the right hand piece. So the first piece, I'm going to have to use chain rule. So I'm going to go over here. I'm going to go over here and find the first piece. So this is the left-hand piece. Y equals u to the 1/2. U equals x plus 1. dy du, du dx.